Okay, so let's get started today. Sorry to be late, won't normally happen, but um, today we are started into the database part of the course. We're talking about the relational model to get into things. Then, after giving you an introduction to the relational model today, which is more of the theoretical underpinnings for it, then we will get into the actual hands-on manipulation of a relational database using SQL. And most of you should have gotten an email message with a database. If you haven't, please let lab staff know about that. It's IT help. If you have not, send email to ithelp at eecs.utk.edu, and they should be able to set you up with a database. We'll go over briefly today accessing it and setting a password, although we'll put off most of that until Thursday and next week. And then after we go through the SQL data manipulation, we do some stuff with the theory. And then after that, we do stuff with database design and physical design. So, getting into things, actually getting this erased. Okay, so basically, Chapter 4 covers what we call the DDL for, it's not showing up there, okay? See if it shows up this way. There we go, is that showing up? Good, okay. So we'll have to do it this way. So the problem is the pen won't work the normal thing, so we'll do it this way. Okay. So what we're covering today is essentially what is referred to as the DDL of the relational database world. So that's the data definition language. And then we won't get to it until we get to Chapter 5 in a couple weeks. But when we get to the relational algebra and the relational calculus, that is the formal underpinning for the query language of the relational model, or the DML. And SQL, in fact, is based on the relational calculus. So as intimidating as that may sound, SQL is actually quite easy to use. And when we get to the relational calculus, I don't think it will seem quite as intimidating as that sounds, because you think calculus, wow, that sounds really difficult, complicated, et cetera, but it's not calculus in the sense that you know it. But today, it's the structure of the database we're talking about, Chapter 4, so that's what is called the DDL. And in the relational model, typically we talk about a relation or table. So we have what are called entities. Here we have branch and staff. So if you remember, the case study we're using throughout the semester is a property management leasing company. And so it has a number of branches and it has some staff. So generally you have what are called entities that you need to model. And each entity will be given its own separate table or relation. So here we have branches, and they're represented by one table, and we have staff, which are represented by another table. And each table has columns, labeled columns. So the branch table has branch number, street, city, and postcode. By the way, the authors of the textbook are Irish, so you'll get some nomenclature that's a little bit different than ours. In the States, we'd call it a zip code. There, they call it a postcode. And you also see some columns for the staff relation. We call each column an attribute. So you see up here, you have 4 pointers. Each column is an attribute. An attribute has a domain. Could be integers, it could be strings, it could be dates. So down here, date of birth is a date. And we'll get to some of the restrictions on relations in a moment, but right now we're just more concerned with terminology. We talk about each row as being something called a tuple or a row. And in the nomenclature that you're familiar with, which is files, we would probably call each row a record. And so we have the columns being attributes, we have the rows being tuples. And then the total number of rows in the relation is called its cardinality. And the total number of attributes is called the degree. So in the branch relation, the degree is what? 4. And what is the cardinality? 5. Very good. Okay, so these are the terms more formally defined. A relation is a table with columns and rows. And that refers only to our logical view of the data. Physically, it may not be laid out this way. It may be laid out as a hash table or as a B tree. So that only refers to the logical structure of the database. Then an attribute is a named column of a relation, and the domain is the set of allowable values for one or more attributes. So a relation is a lot like a struct in C or a class in C++, and the attributes are a lot like variables, and the domains are a lot like what? Carrying that analogy to its conclusion, types that you declare your variables to have. So essentially, there's a nice mapping between structs or classes, which you are familiar with, and relations which perhaps you're not so familiar with, although this is part of where 311 comes in. You should have at least been introduced to relations in 311. So a tuple is a row of a relation. So we just said degree is the number of attributes in a relation. The cardinality is the number of tuples in a relation. And then the big thing, a relational database is a collection of normalized relations with distinct relation names. So there's a couple key terms there. The key terms are normalized and distinct. So the relation names have to be distinct. That should be pretty clear. In a program you write, your classes or struct names have to be distinct. What normalized means is this bullet point right here. It means that when the column or the relations have been normalized, then typically the only shared columns or redundant data are the ones involving so-called foreign keys. And we haven't talked yet about foreign keys. In fact, I'll go back. Let me go back to the slide right here. And you actually did see that there was something labeled foreign key there. So let's just talk about that briefly right now. A primary key is one that uniquely identifies each tuple in the relation. So here, branch number is the primary key. It uniquely identifies each tuple in the relation. A foreign key is a key that uniquely identifies a tuple in another relation. It allows us to link two relations together. So in this case, if we want to find out which street John White works on, we'd first find in the staff relation the branch number that John White works at, and then we'd use B005 to look up the corresponding branch, and we'd find that John White works at 22 Deer Road. So foreign keys are like navigation links, a bit like hyperlinks on the web. They allow you to jump, in effect, to another relation to find out additional information. And that way we don't have to redundantly store information in our relations. So we could conceivably have stored the street address and the city and postcode for branch 5 right here in the staff relation, but then we would have redundant information. We would have stored street, city, and postcode in two different places, so we don't want to do that. So we say that a relation is normalized when the only shared information is essentially the foreign keys, the links between relations. And if you look at the lecture notes, you'll see that at some point there's a week devoted to a discussion of normalization. So there's a formal algorithmic way of ensuring that relations are normalized. But a relational database then is a collection of these relations. Okay? And I'm not going to spend a lot of time on examples of attribute domains other than to say that in a database they are richer than the set you're used to in a programming language. For example, dates are important in databases, and therefore dates are a primitive type in most database systems, including in MySQL. And also, it's important to often be able to define your own custom types. For example, we might want to say that a branch number is something that starts with the character B followed by a 3-digit integer, and be able to define that as a type. And so many database definition languages give us the ability to actually define new types. I guess much like a class, but a class doesn't really restrict a type. In this case, we're kind of specifying a pattern for that type. Okay? For those of you who are familiar with regular expressions, if you're not, don't worry about it. But for those of you who are familiar with regular expressions, sometimes DDLs allow you to use regular expressions to define new types. Okay, so with each attribute you have a type. And then there's a number of different ways to refer to the important elements of a relation depending on what view you're taking of it. So if you're a researcher and you're discussing it formally with another researcher, you will use the terms relation, tuple, and attribute. If you are a customer and user, you will use terms like table, row, and column. And if you are the database administrator who is physically implementing the relations on the file system, you will think in terms of file, records, and fields. That's probably the level that you have been thinking of it up until this point. In 302 or 140, you thought of a file. Each line of the file might have been a record, and then you broke each line into fields. But that's a very low-level view of data in a database. The higher level view is as table, row, and column. Then, as I said, the formal theoretical terms are relation, tuple, and attribute. So the way to read this table is to go across. So relation, table, and file are all synonyms. So is tuple, row, and record. And attribute, column, and field are all synonyms. And I will use them interchangeably. Okay, so there is a mathematical definition of a relation. And it is as the cross product of a series of domains. So a relation is actually a cross product of domains, and you'll see in a moment, with each domain, it has to be labeled with a name. So very simply, if we have just two domains, D1 and D2, and we've limited the domains, here D1 is the even integers 2 and 4, and D2 is the odd integers 1, 3, and 5. In this very simple example, the Cartesian product, which is being butchered by PowerPoint, because that is supposed to be an X. Wow. Really being butchered. Okay. It's fine. Just messing it up. Don't want to use symbol. How about giving me another choice? There we go. We'll just use times for the hello. Okay. There we go. Should be an X. So the Cartesian product is simply all possible combinations of the elements from D1 with the elements from D2. So there's 6. This should be an X down here too. It should be D1, X, D2. I don't really know what PowerPoint is doing. At any rate, you can see that we have here the 2, and it can be combined with any of the 3 elements from D2, so 2, 1, 2, 3, and 2, 5. And then 4 right here can also be combined with any of the elements 1, 3, and 5. So we get 6 potential elements. Now that's just the space from which we can draw tuples. This isn't a relation itself, it's the space from which we can draw tuples. So a relation would be any proper subset of these 6 tuples. Okay? So for example, here is one such relation consisting of 2 of those tuples. Now, you can theoretically place constraints on the tuples. So I could say the relation is all tuples x and y such that x is part of D1, y is part of D2, and y is equal to 1. Well, looking back here, we see that 1 can be crossed with either 2 or 4. Therefore, the relation in this case would be those 2 tuples. Or we could say that the relation is a set of tuples such that x is equal to 2y. Well, if we look at the possible set of tuples here, there's 6 possible tuples. There's only one, this one right here, where x is twice y. And so in that case, we're restricted to this particular relation. Now, in practice, we never specify our relations this way. But you are computer science majors for the most part, and you should be aware of the formal underpinnings of the model. And formally speaking, we can write relations and specify them this way. Basically, we are writing constraints on the relation. And you may remember from last Thursday, you can put constraints on a relation, such as no one makes more than $40,000, or no property manager manages more than 100 properties. So in fact, it is useful to be able to have this kind of formal element of being able to constrain the tuples in your relation, even if we don't do it in this rigorously formal way. But the capability is there. Okay, so questions about that? Okay. So you can continue and do it for 3 domains and then up to 4 domains. And again, those apostrophes should all be X's. So a general relation is a Cartesian product of n domains. They don't have to be distinct or unique, but once you apply a label to each of the domains, they must be distinct. So for example, going back here, it's not both the city and the street could be strings. So they have the same domain. But then once you label them, they must be unique. You couldn't use the label street twice in the same relation, although you could use it in 2 different relations. Okay, so we take the Cartesian product, usually written like this. So that's the product symbol over these n domains. And any subset of those n tuples from this Cartesian product is a relation. Okay, now in practice, our relations are not specified this succinctly. Instead, it's simply an enumeration of the tuples, okay, which is what those branch and staff relations were. They were simply an enumeration of tuples. Okay, so a database relation is got a number of specific characteristics. First of all, a relation is a named relation defined by a set of attribute and domain name pairs. So that's where I was saying that every domain gets associated with an attribute name. And the attribute domain name pairs must be unique for that relation, just like they would be unique in any class that you defined. And then we say that a relational database schema is a set of those relational schemas. And you may remember last Thursday we talked about catalogs. We said that there should be a user catalog. Okay, this is the user catalog. The set of, it's not necessarily complete, but it is pretty much so from the user perspective. So the relational database schema is the user catalog for that database. Okay, it specifies the name of each relation. It specifies for each relation the attributes, with each attribute having a name and a domain type. From that, users should be able to pretty easily create queries. Now, this isn't sufficient for a programmer. A programmer is going to need a little more information, such as perhaps the number of characters in the string. But generally, the user wouldn't need to know it at that level of detail. Okay. Then these are all things that must, it says properties of relations. These are thou shalts. Okay? These are the, just like the 10 laws were given to Moses, these are the, I think, 7 or 6, 7 immutable characteristics of relations. Okay? So a relation name is distinct from all other relation names in the schema. So that means within a database, every relation name is distinct. An important restriction is that each cell in the relation contains exactly one value. And that actually is a fairly major restriction and inconvenience of the relational model, because we frequently find that we actually want what are called multi-valued attributes. And we are not being permitted to use multi-valued attributes. So basically, what this says is that multi-valued attributes are not permitted. So multi-valued are prohibited. That's a pretty big restriction, and there's ways around it that I'll show you, because multi-valued attributes definitely exist. Multiple phone numbers are a common one. You might have a set of friends. That's a multi-valued attribute. You might have, let's see, multiple cars or dependents. If you have dependents, you might have multiple dependents. So these are all multi-valued attributes that you cannot store, because a cell can contain exactly one value. So you can only store one dependent or one phone number. Again, there's ways around it, but this is a very important restriction in the relational model. Okay, it's probably the one that is the most irritating. Yep, that's what you do. So, Luke, you're right. That I didn't want to get to it yet, but essentially the best solution is you form another relation with a foreign key, and that relation has all the multi-valued. So for dependence, you'd form a dependence relation. The foreign key would be your, say, student ID or employee ID, and then you'd list all the dependents. You could list as many dependents as you wanted. Now each is a separate tuple. But it's a little clunky. Okay? But the reason for doing that is it gives you a nice table, only one value per cell, and it makes it easier for the database to store information and to manipulate it. Okay? Each attribute has a distinct name within a relation. Two different relations can each have the same attribute name. So I can have owner and client, and each of them can have an attribute called name. But I can't have name appear twice within the owner relation. So within a single relation, each attribute has a distinct name. The values of an attribute are all drawn from the same domain. Again, that's sometimes limiting. Sometimes, for example, you would like an attribute to be either an image or a label, and you can't do that. It has to be always the same value, or the same type. So it may be all images or it may be all labels, but it can't be one or the other. Tuples must be distinct. There are no duplicate tuples. Okay? That if you have duplicate tuples, you can't really distinguish them. So it kind of creates a bit of nonsense. That's why they disallow duplicate tuples. And the order of attributes has no significance. So you can put them in any order you wish, which is different from the mathematical definition of a relation. So sometimes the mathematicians in the course get a little confused, because in 311, the order of the columns mattered. But in a database, the order of the columns does not matter. So in our database, it doesn't matter whether branch number is the first column or the fourth column. It's the same relation. But in 311, if I gave you this version of branch number, and then I also gave you the version street, city, say branch number, and postcode, those would not be equivalent. So in 311, those two relations would not be equivalent because order matters. But in a relational database, order does not matter. That clear? I'm guessing that when you were in 311, that little nuance went over your head anyhow, but it is the case. Okay, so then we have, and the final one is just like the order of the attributes has no significance. So we don't care how the columns are arranged. We also don't care how the rows are arranged. So 6 says we don't care about columns. 7 says we don't care about the order of rows. Now, in practice, the database administrator cares deeply about the order of the rows because it affects the efficiency with which queries are answered. So you know in 302 certainly what was one of the big kinds of algorithms you were taught in 302? Sorting. Because sorting allows us to retrieve data much more efficiently. So in practice, we do tend to order our tuples according to some key or some attribute. Oftentimes, it is not on the so-called primary key, which we'll get to in a moment, so I'll put off that discussion. But just from a theoretical standpoint, the order of the tuples is immaterial. From a practical standpoint, it's very important because it affects the efficiency with which queries are answered. So we move into keys. So keys are unique identifiers. They uniquely identify a tuple in a relation. And there are a number of different terms we give to keys. So first of all, a superkey is any attribute or set of attributes that uniquely identifies a tuple within a relation. What guarantees, what is always a superkey? Given a relation, any relation, what is guaranteed to be a superkey? The what? Primary? Nope, you're jumping ahead. Primary key is a different concept. I'm just asking what set of attributes is guaranteed to be? The set of all attributes. And why is that? Because according to property 5, each tuple is distinct. Therefore, if you use all attributes in a relation, you are guaranteed that together they uniquely identify that tuple. Therefore, one superkey is the set of all attributes in a relation. Now, that's not a very useful definition. We actually prefer a so-called minimal key, which is the minimal set of attributes from that set that would be capable of uniquely identifying each tuple. We call such a set of attributes the candidate key. So it is a superkey such that no proper subset of that key is a superkey. So what it means is if we say that, let's get rid of, if we say that we have 3 attributes, A1, A2, and A3, if that is a candidate key, then no proper subset of that can uniquely identify every tuple. So it means that A1, A2 by themselves can't, A1, A3 can't, nor can A2, A3. That if we dropped any one of those 3 attributes, we would no longer be able to uniquely identify every tuple. So a candidate key is in some sense a minimal key for that set of attributes. So it has those two properties that the first one is they uniquely identify each tuple, and it's irreducible in the sense that we cannot remove any attribute from that set and still uniquely identify each tuple. Now, there can be multiple candidate keys in a relation. So let's illustrate that. So that may not be obvious. Let's actually do this one. So here is one for hotels that we will use fairly frequently in the homework assignment. So you can see that one is hotel, listing hotel, name, and city. Another lists all our rooms. Another lists all of our bookings. Another, for those of you not familiar with the term booking reservation, it's another term. And guest, a list of all of our guests that have stayed with us past, present, or future. So in this case, what might be a candidate key for hotel? Based on, just use intuition. Pardon? Hotel number. So often we are given what are called artificial keys. Hotel number is an artificial key. Okay, it is a made-up field. Unlike things like our last name, our first name, our street address, our salary. Those are, in some sense, natural or real fields, but they may not uniquely identify tuples. So last name is not going to uniquely identify many of us within the university. Even with last name and first name, it doesn't uniquely identify everybody. Okay? Even last name, first name, and middle name may not be enough. So we often want to have a fairly compact field that will uniquely identify tuples. And so we make up keys like social security number or student ID or customer ID, or in this case, hotel number, to uniquely identify each tuple in a relation. Okay? If we look at guest, again, guest number is going to be a pretty good primary key. It's a made-up key that is going to uniquely identify each tuple in the relation. Now, let's look at the other two. Let's first look at room. Is there any one attribute in that? So type might be double, king size, suite. Do you think there's any one attribute in that relation that uniquely identifies every tuple in the relation? Probably not, because we can have the same room number in different hotels. So room 103 could easily be in multiple hotels. Okay? And clearly every hotel should have multiple rooms, or we're probably going bankrupt pretty quick. Okay, generally, a type is not going to uniquely identify a room, because typically we have multiple rooms of each type, and we don't typically uniquely price our rooms. So we can't, one key by itself is not, or one attribute by itself cannot uniquely identify. Now we know that all four uniquely identify, but can we do better? We can. Throw out a suggestion of what subset of the keys together can uniquely identify? Room number and hotel number together should do the trick. So in this case, the candidate key is actually two attributes, room number and hotel number. We require both. Now we could make up a unique attribute, but I didn't because it drives home the point that you don't need an artificial key. You can actually construct a key from multiple attributes. Okay, let's go to booking, which is a reservation. Okay, we're going to make some assumptions. First of all, we can't double book a room. So we can't have two people in the same room on the same night. Okay, and we're going to make another assumption, which is we're not going to allow, this is weaker, but we'll make it, we won't allow a guest to have two separate reservations on the same date. I know that's a weaker one because many hotels allow it, but we're going to make those two assumptions. So given those two assumptions, there are actually multiple potential keys here. That's why they're called candidate keys. There's actually more than one potential key for the booking relation. Okay. Start by telling you that there is no one attribute by itself that uniquely identifies every tuple in the booking relation. So can someone suggest, now we are allowed to have multiple reservations on different dates. Okay, so can someone suggest a set of attributes there that will uniquely identify a booking? Okay, guest number and, okay, very good. Given the restriction that I said that no guest can have multiple reservations, guest number and date from is a candidate key. But it's not the only possible key. What's another set of attributes that will uniquely identify a booking? Yes, Michael.
How about hotel number and date from?
Okay. You are close, but you need something more because hotel number and date from by itself, we can have multiple guests. Room number. So if we add to that room number, that is another candidate key that uniquely identifies every tuple in the relation. Okay. But wait, there's more. Okay? Can someone suggest another candidate key? Guest number and date too. Very good. So guest number and date from was one. Guest number and date two is another. And we have also that hotel number, room number, and date two. But wait, there's more. What's another one? There's one more. Yes.
Guest number, date from, date two.
Guest number, date. Okay, so if you say guest number, date from, and date two, that's what's called a super key, but it's not a candidate key because it's reducible. Okay, because I can remove one of those two attributes and I'll still have a candidate key. So you were right in that it was a super key, but not a candidate key. Yes.
Go ahead. Hotel number, room number, and date from.
Very good. So hotel number, that might have been yours, Michael, but it's the other one, so date from. Okay, so the 4 different candidate keys. That's why they're called candidate keys, because they're all candidates. All 4 of these uniquely identify a tuple in the booking relation. And notice that even though these two keys are bigger, they have 3 attributes, than the first 2 keys, they're still candidate keys. So a candidate key doesn't say that it is the smallest possible number of attributes, period. It's the smallest number of attributes given that set. Okay, I can't remove any attribute from these 2 and still have a uniquely identifying key. So it's a candidate key because I can't remove any attribute from this set. Now clearly this might be the better key. One of these 2 might be better because it's more compact. But all 4 are candidate keys. Okay. Now in practice we know that most people you're given a confirmation number, and a confirmation number is really a booking number. So in the real world, probably there would be a so-called booking number here, but I omitted it intentionally because I want you to have to see that there are multiple candidate keys and why we call them candidate keys. Okay, because they are exactly that, candidates. Okay, so a primary key is the candidate key selected to identify the tuples uniquely. The other ones now are just candidates, but we select one of the candidates to be the primary key. So for example, in booking, we might select guest number and date from. That's a little more natural than guest number and date to. When you call up and say, I want to cancel a reservation, no one ever says, what day were you checking out? Right? They always ask, what day are you checking in? So you'd probably choose guest number and date from. And then the remaining candidate keys become alternate keys. Okay? So they're still all primary and alternate keys still have the name candidate. They're still a candidate key, but then we select one of those candidate keys to become a primary key, which makes the remaining candidate keys alternate keys. Now, so we had super keys, then we had candidate keys, and then from the candidate keys we selected a primary key. A foreign key is a different animal. So we talk about orthogonality. A foreign key is going to be a set of attributes that matches a candidate key in another relation, or actually sometimes it's the same relation. So a foreign key matches a candidate key in another relation, or actually sometimes the same relation. For example, in the staff relation, we might have a manager field. In that case, your manager would be a staff number, and it's in the same relation. Okay, so foreign keys are, like I said before, essentially a link, like a hyperlink to another relation, allow us to pull in more information. They typically denote a relationship with another relation. For example, staff work in a branch. So that is a relationship between staff and branch. In the hotel relation, okay, a booking is actually a relationship among a guest, a room, and a hotel. A person books a room, or a guest books a room at a hotel. So booking actually represents a 3-way relationship between a hotel, a room, and a guest. And sure enough, hotel number, guest number, and room number are all there as foreign keys. There's 3 foreign keys there: hotel number, room number, guest number. Okay? Or room has a hotel number as a foreign key because a room is part of a hotel. So foreign keys denote relationships with other relations. Okay. So questions about that? Okay. Let's take a break for a moment because it's always good to do that. Attention spans are usually about 20 minutes, and I'm well over that 20 minutes. So, want to take a break. I'll come back to this, but what I'm going to do now is invite you to open your laptop and work along with me. I'm going to show you how to get into your SQL databases. So each of you hopefully was sent email, and to do this you will have to log into a Hydra or a, is it a Tesla machine, or did they change the name? Okay. So a Hydra or a Tesla machine. If you are from another department, you may need to talk to me or a Elvis or Jaja about getting an account, because you will need to be able to log into the Hydra and Tesla machine. So if you can't log in right now, don't worry about it. I did see that someone posted a message to Piazza asking how to connect via PuTTY. If someone could, perhaps, I'm actually not super familiar with PuTTY, but if someone who is familiar with PuTTY, if they could give some simple directions or a pointer to PuTTY, I would appreciate that. That would be very helpful. So some of you may have to connect via PuTTY. It's a program that Windows users can use to connect with our machines. So I'll go ahead now and just do that. So the name of the command is MySQL. Once you're logged in, it's MySQL. Then you give the name of the server with the -H flag. So -H just says I'm naming the database server, which is dbs.eecs.utk.edu. Then you need to give your username. So you give the -U to say this is my username. That in this case it's B Vander Z. Then you want to ask it to prompt for a password. So by, oh, come on. What the? How is this? Okay, there we go. Wow. Okay. So if you want it to prompt you for a password, so say -P and then the name of your password. Every one of you was given a unique password, and of course I've already forgotten what mine is. So mine, great, somewhere here. It's going to be down here in CS465. Okay, so my password is this one. Okay, so you enter your database, and then what the? Why didn't you prompt me? Come on. MySQL H. Okay, we'll do it different. I don't think this should make a difference, but could. Okay, that's weird. I don't see why switching the order of the flag should make a difference, but it did. So I had to put the -P before the -U. So just jot that away in your memory banks, because doing it in the opposite way didn't work out. So enter your password, which you were given some incomprehensible one. And the first thing you probably want to do is change it. So the command to do that is set password equal to password. and then some new password, whatever you want. I'm not going to do it, but that should change the password to something you can use. And you need to put a semicolon at the end of it. If you forget to do that, I really don't want to change the password. So see how it gave me an arrow? It means the incomplete. It's asking for more. In this case, it's missing a semicolon. Yes.
My randomly generated password begins with a bang,
Mm-hmm.
and so it's looking for the event. String statement.
You should be, can you do a backslash?
I can try that. Mine had grid leaders too, so I put it in strings. So it's like in single quotes.
So if you have a bang, an exclamation mark, or bang character at the begin, try using a backslash. That's interesting. I haven't run into that. So when you, pardon?
It freaks out for number signs too.
Okay, so it means when it prompts you here, if you're given a bang sign as your password, when it says password, you may have to put you may have to type backslash first if you have either an exclamation mark or a pound sign. Okay, so just in that case, I type a backslash first and then your bang sign.
I had to string scrape mine in the line above too, actually. Like I had to put single quotes around the where yours is COSC like that part.
Really?
Yeah, because I had a pound sign there and it freaked out.
Huh. Okay. I'm surprised you had a pound sign there. Weird.
I have all kinds of weird characters.
Okay. So if you have weird characters, put quotes around it. Now, when you entered your password, did you actually start the password with a quote or with a
No, I
backslash?
haven't got that to work yet. I was like
If you just dash P and you don't put a password in, it'll prompt you for the password.
Right.
You can enter it without any.
Oh, okay. Oh, okay. So it turns out if you just put dash P like I did, and then you enter the password you don't need. Okay. So once you're in,
Is that password equals password function in quotes, then you put that string?
yes, whatever string becomes your password. Okay. Now, you may want to populate it and actually have so if you say source and then in parentheses the name of something, so we'll say courses 2000, see it's just 465, I think lectures create db.sql. That didn't work, so let's find the name of it. There we go. Okay, so if you enter this particular string right here, and I'll type it out so you can see it. So we're going to say source. Whoops. Now I've got myself in a bad way. Okay, let's try this again. So if we say source, whole thing, and create db.sql, this sucks in a file of commands that I have already done to create a database. Still failed to open it. Why? Oh yeah. Let's see. I need single. Does it not want quotes at all? think it wants quotes. Maybe it wants single. No. Oh, it's not the same file. Yep. Okay. It is. I need an SQL in here. There we go. That's what's causing the issue. Still. Okay, let me look at my notes. My notes say, so if you go to the lecture for 831 and 9.5, Getting Started with MySQL Database, it has all this information. And in fact, I didn't need quotes. Great. So there were no quotes after all. So that was the problem. Let's get rid of those quotes. Oh, come on. Now what's the problem? Thank you. Good to have a whole set of eyes there too. There we go. Okay. So, whole bunch of commands get executed. I won't go over those commands yet. I'll go over them probably on Thursday. But you can do some useful things now, like show tables. So it created 3 tables: courses, student, and student courses. So that command again was show tables. And I could look, again, don't worry, this is a query I don't expect you to know, but I'm selecting star from courses, and as you can see, I populated it with some data, and it produces a nice little relation with course ID, course names, locations. So MySQL is an interactive interpreter that you can use to enter commands. Okay, you can also choose to look at the schema for a particular relation. So the describe command will list the schema. So here we have field type. Null, we'll get to that in a moment, what nulls are. Whether it's a key, if it were a key, there would be an asterisk here. Whether it has a default value, in this case it doesn't. So those are some of the basic commands, and then if you want to get out, you say exit. Okay, that's all we're going to do for the time being. So just some basic commands to get set up. If you didn't follow all of that, you can go to this Getting Started with your MySQL Database from the lecture notes for Thursday, and you can do it at your leisure or once you have an account established. Yes, Axel. Eventually for the homework assignment, you'll need to do that for the hotel file. In fact, if you look at the supplementary files for homework 1, it actually has a script that creates the hotel thing for you. Pardon? Well, for the one I just did, I also do some queries during class, so it doesn't hurt to create those too. Okay, I'm not done. I got a few minutes, and with those few minutes, I'm actually just going to run through one more thing with the relational model, and that is that you have what are called integrity constraints. You just saw this, null. Oh, yes.
Really quick, I tried to do what you just did in my SQL. It says it couldn't be taken in the file. I think Nathan was having the same thing.
Might be permissions. Let me check to see if.
And then also, is the 2017 supposed to be in there? In your notes, it is not.
Yeah, I think I'm going to have to do one of two things. Either put a link, or I'm going to have to. I think it's going to work because I have a symbolic link with CS465. I think the issue is I didn't set permissions.
Okay.
So I will do that right after class. Okay. So you saw that null. Going back here, it was saying, is null a legitimate value? It said yes. So what does that mean? Means that I can't get, what the heck? means that my Macintosh and the projector are not playing nice. Okay, there we go. How about, won't let me have it. Okay. There we go. There we go. Okay, so null. What does that mean? If you use null, it means that there is no value currently known for that attribute. It doesn't mean that there isn't a value, simply that one is not yet provided. For example, we might have a comment attribute for viewings. We might have a viewings relation for our leasing company. When a client views a property, the leasing agent or sales agent fills out a little tuple, puts in the relational database. One of the attributes might be a comment the client made. If the client made no comment, we make it null. If the client gave a comment, we put the comment in. So null simply represents an incomplete piece of data. It's an absence of a value. Generally, if you have a large number of nulls, you might want to split that off into another relation. We'll talk about that later. It's not important now. There's also something called entity integrity. It means that in something called a base relation, we'll get to base relations on Thursday, no attribute of a primary key can be null. Makes sense. Primary keys uniquely identify a tuple. If you have one of the attributes in a primary key be null, that's not going to do a good job of uniquely identifying anything. So entity integrity means that in a database, relational database, we don't allow any part of a primary key to be null. Okay, so we need to be able to uniquely identify our entities. Referential integrity refers to the fact that if you have a foreign key, the foreign key is either null or no field in the foreign key may be, well, actually, it's either wholly null or else it matches a primary key in some other relation. So a foreign key could be null. For example, we might have a staff member who's new and is not yet assigned to another branch. We would put null for that staff member, so that's valid. But if they do have a foreign key, then it must refer to the primary key in some other relation, and that primary key must exist. It can't refer to a non-existent key. It makes sense. If we have a staff member, we can't assign them to a non-existent branch. That would be bad. Okay? And by extension, foreign keys can't have null in them. Why can't foreign keys have a null in any attribute? They can be null completely, but if they are specified, why couldn't they have a null in one of their attributes? Because the primary key can't have a null. Therefore, the foreign key can't. Okay, and then we have general constraints. Those are so-called business constraints. So for example, no one can have a salary that exceeds $100,000. The memo came down to me over the weekend that we're being cheap at $40,000, so we need it to be $100,000. Or no property manager can manage more than 100 properties. So we call those general constraints. Those are additional rules specified by the user or the database administrator. The first three are inherent to the relational model. They are part of the theoretical model. The fourth one is part of it too, but those are user-defined as opposed to being part of the model itself. Okay, we will pick up on Thursday with views, and we will also get into the SQL language on Thursday.
So, quick question. It says you can use Unix commands,
Oh.
right? We use things like grep.
Yeah.